So welcome everyone. Today is the fourth day of the school. So the first lecture is by Dario.
Hello, can you hear me? Good. Okay, good morning everyone. Thanks for being here. I see that it's harder and harder to get up and come here at this time. But nonetheless, we shall go through the lecture. There were some questions yesterday after the class, so I would like to touch upon some of the points, review some of the aspects of the topics that I talked about yesterday. And then we will try to do time evolution for using matrix product states, at least in one way, maybe two or three, and depending on the time. And then we will start to talk about neural network quantum states. Okay, so that's the plan for today. Let's start with what we tried to do yesterday is to solve, to optimize matrix product states such that it will solve the Schrödinger equation. And so in this way, find the ground state energy and the ground state property. Because once you get the MPS, you can extract properties. Okay, so one question that there was, for example, was suppose I have this matrix product state, and now I'm not looking at a local observable, but I'm looking, let's make it longer, okay, so that it's clear. But I'm looking at some correlation. So for example, I have an operator here, and another operator here. Okay? And then of course, I need to close it. Here I have all identities, so that's easy. Ta-ta. In this case, can you compute this very efficiently? At the end of the day, no. You can save something by saying, okay, I have some mixed canonical representation, for example. Then you have a single value here, then maybe BBs all the way, for example. And here you can simplify, all of this portion becomes identity like this. Then you have your tensor here. Tack. And you have identity here. Okay, and you have your local operators here. But all of this part you need to contract it. There is no way to simplify this afterwards. Okay, so you need to contract it, and then. But again, since it's in 1D, it can still be done quite efficiently, right? It's not instantaneous. Fair enough. And so let's say many people want to look at how correlations decay in space. Okay, so you will take two operators here, and then here, and here, and here, for example. On a very large systems, then you try to find like correlations as function of distance. Okay, so for this case, there is, let's say, a non-instantaneous but still efficient way to compute the correlations. Okay, so this was one question. Another question was about before we go to the next question, maybe I review how we computed the ground state. Okay, so I have this MPS. Okay, and here I give you the MPO of the Hamiltonian. Okay, I say, okay, this is the MPO that represents the Hamiltonian. And if you remember, I was saying that there were some tensors here, W. Okay, but I didn't describe to you at all how this can be built up, right? And so maybe you can spend a few minutes to try to do that, because it's quite important. Okay, so there are ways to construct exactly, okay, the MPO for certain Hamiltonians. Okay, and for example, we can take the Hamiltonian H equals to sum over L of minus HZ sigma Z plus L, J over 2, sigma plus, sigma minus, L plus 1, yes, plus sigma minus, sigma plus, okay, and then maybe J, Z, sigma Z, L, sigma Z, L plus 1, okay. Quite straightforward. This is a XXZ model, okay, plus field. Is this correct? Just to make sure that I'm using the correct Hamiltonian. Yes. Okay, so to build this, I'll give you the solutions, and then we can try to work out that the solution actually works. Okay, we do it like that. So the first MPO will have identity here. Okay, let me just take the notes. So I don't. Oh no, already wrong. Minus H sigma Z. Okay, then J over 2 sigma plus sigma minus J over 2 sigma plus JZ sigma Z identity. So this is on the first side, so let's call it W1. Okay, in the center, all of the others, okay, except one or the final one, will look like this. Identity, sigma plus, sigma minus, sigma Z, minus H sigma Z, okay, and then, yes, J over 2, sigma minus, J over 2, sigma plus, JZ, sigma Z, identity. Okay, and the final one, to close the shop, will be vertical. Yes, you have 1, sigma minus, sigma plus, sigma Z, minus H sigma Z. Okay, so now let's put the indices here so that it will be clearer how this works. So this is L, and this is final L, capital L. Okay? So now this looks a bit mysterious. The first time I saw it, it's like, okay, seems a bit out of, but there is a clear logic. And we can try to build it up. So these are, let's multiply, for example, W1 times W2. Okay? So you do this times this. Now, as soon as you do this times this, you can see that your first term, minus A sigma 1 appears. And then you will have sigma minus times sigma plus. Sigma plus times sigma minus, sigma Z times sigma Z. And then you carry forward the sigma Z for the next site. So in the first element, you start to build up the Hamiltonian. And then, for all the other elements, you see you will have identity times this, identity times this. So you will carry forward what you did for the next site. Okay? And you build up, Huh? Quite cute, huh? So sigma 1, then, so let me write it. J over 2 sigma 1 plus minus sigma 2 plus J over 2 sigma 1 plus sigma 2 minus JZ sigma Z 1 sigma Z 2, and then minus H sigma Z2. This is the first element. Okay? And then I build up, I've read below the other elements, but imagine this is a row vector. So I will have identity times this, So you have Jz, j over 2 sigma minus 2, comma, j over 2 sigma plus 2, comma, j over z sigma z2, and identity. Okay? And now you can see how this continues, right? Because the next step, you will do this times identity, so you just carry it forward. But then you'll have this terms times this, so you have sigma 2 minus sigma 3 plus. Then you have sigma 2 plus, sigma 3 minus, sigma z2, sigma z3, and then the field. Okay, when you do this times this line. And then, with the identity, you will carry forward all the other terms in all the other elements. And then at the end, you close with the last one, and you get the last fields. Okay? Is it clear? Okay. So, and you can also build this, use it to do maybe next nearest neighbors. Then you use some identities, some operators here, and identities here, so you can carry forward the next. So there is a way to carry forward also nearest neighbors, and there is a way also to build other shapes of MPOs analytically. Okay, so that's fun. And if you want to play on building up MPOs analytically, a few years ago we also built MPOs to represent cellular automata evolutions. Okay, then we use that to do some kind of a machine learning task. So that and there are many nice works by a lot of people, especially in Ljubljana, working on how you can build these MPA matrix products, ansatz, and so on. So there is a lot of analytical results that you can build nice solutions. For example, solving non-equilibrium models, steady states, using quite advanced and nice ideas. Anyway, so you can build a Hamiltonian like this. But the other way that can also be very convenient is to, since the Hamiltonian is a sum of some local, let's say, bond Hamiltonians, okay? I write HL to say it's some bond Hamiltonian, or some terms of Hamiltonians. So you have many, many terms. This L doesn't go on the sides, goes to the various terms that you add in Hamiltonian. Okay? Each term of the Hamiltonian, you can write it as a bond dimension 1 MPO. For example, if sigma z, even if it's long range, okay? Let's say HL is equal to sigma z1, sigma z10, okay? Okay. You can still put identity. So this is identity everywhere. It's an MPO of bond dimension 1. Okay. So once you have all the terms, what you can do, you can add up MPOs. So you have an MPO. Okay. So this is a matrix product operator. Okay. And you can, let's say, call it 1. And you can have another MPO. And you can add them up. Now, how do you add up MPOs? Okay, let me show you. You add up MPSs, and then you can figure out easily how you end up MPOs. Add the MPOs. And after you add the MPOs, you will see the bond dimensions of the new MPO is larger than the previous one. It actually is the sum of the bond dimension, and you can choose to contract as well. Okay. So I'll show you how to do this by adding MPSs, and then it's kind of straightforward to carry to the addition of the MPOs. So I have an MPS, and let's write it like this. It represents a wave function, 1, okay, and then you have sum over the various sigmas, and then let's say M sigma 1, M sigma 2, M sigma L. Okay, and then I have sigma 1, sigma 2, sigma L. Okay, so now let's say you have an MPS 2. Also sigma. And let's call it N. No, M tilde. Sigma 1, M tilde sigma 2, m tilde, sigma L, sigma 1, sigma 2, sigma L. Okay?
Sir,
Yes? Yes.
sir, before you go on, I didn't get the multiplication W1 and W2. W1 is a 1 cross 5. W2 is a 5 cross 1 matrix. W1 into W2 you are getting, I think, 1 cross 5.
Oh, did I do? No, no. So this, each element is, of course, an operator, so but it doesn't matter for now. I do this times this plus this times this plus this and this line times this column gives me the first element, right? Okay, let's put it this way. Element 1, which is going to be here, is going to be this times this, right? Okay, and then the element 2 is going to be this again, there is a, times this. Now it's difficult to read what I wrote here, but you got the idea of what you're trying to do. Is it clearer now? Okay.
Or this empty space.
It's zeros.
Can you say that how to do in case of PVC this W capital L and W1?
P, periodic boundary conditions.
Yeah, in case W capital L and W1. Because I have interaction between those two sides.
Yes, for periodic boundary condition things are a bit trickier, of course. But what you can do maybe is the other method. We'll add up the MPSs and the traces. Okay? Okay, so we have something like this. Now, you realize that I can build something like this. M sigma 1, M tilde sigma 1, M sigma 2, M tilde sigma 2, M sigma 3, M tilde sigma 3, M sigma L, M tilde sigma L. Okay? Once you do this, what you're getting is really the sum of these two things, right? What you need is the sum of the two wave functions, right? And so you do this times this, you get this times this, and zeros. Plus this times this, right? And then the other element is this times this. Then you continue. All the m's add up to each other, multiply with each other, and all the m tildes multiply with each other, and at the end you have the sum of the two. Okay? And you can do the same with MPOs, but what you do, is that, okay, so let's write it a bit more clearly. We have omega here, maybe sigma L prime, and then for the auxiliary indices I use B L minus 1, BL. Okay? So this is sigma L prime, BL minus 1, BL. And what you can do is to think about it. You can think about it this way. You combine the two physical indices, sigma L prime. I keep here BL minus 1, I keep here BL. Then this is really the same as an MPS. Then you can do all the machineries that you build for the MPS, you can build it for the MPOs. And like this, you can add them up. Okay? And when you add them up, then what you see is that the bond dimension of this adds up to the bond dimension of this, and you get the bond dimension of the sum is the sum of the two bond dimensions. Okay? And then you compress it. Cool? This part here? Okay. So at the end of the day, it's up to you how you organize your indices, okay? As long as you do it consistently, carefully. And so instead of writing in this form, okay, I can combine these two indices, the physical indices. I can basically bring this up one, okay? And now I have basically an MPS. And so when I add an MPOs, I can you can think of I'm adding this MPS. So then you see that the machinery will be the same. Okay. And for the compression as well, the way you compress the MPS, you compress the MPOs. Sounds good? Okay. Boom. Okie doke. The other thing I wanted to, so now you know how to build an MPO. And there was another question about the compression, about finding the eigenstates when I have two sites. When I do the two-site optimization instead of one-set optimization. And that reminds me that maybe I can address another interesting aspect. So I have the MPO somewhere in the middle. I want to do my optimization. Okay, and instead of optimize on a single site, I optimize over two sites. Okay. When I optimize over two sites, okay, I get an object. Let's say here I have a bond dimension D, and here a bond dimension small d and small d. Correct? Small d for the physical, large d for the auxiliary ones. Then my solution will be something like this. Again, with bond dimensions, small d, big D, big D. Okay, let's call it, how did we call it? I forgot. Let's call it phi, AL minus 1, AL plus 1, sigma L plus 1. Okay, and now what I told you, let's say we're going, let's say we're sweeping to the right. Okay. What I can do is a singular value decomposition. So I will have a U, AL minus 1, sigma L, comma, AL. And then I have the singular values, AL, AL. And then I have V dagger, AL, sigma L plus 1, AL plus 1. I hope you can see this thing hidden here. Okay? And this portion here will become my new A. AL minus 1, AL. Okay. Now you notice, and then I told you that this part we can discard it because once you optimize the first one, then later on I will try to optimize the next two sites. Not the first one. Yeah. Yes. Okay. So this one will be kept and brought it here to update the left environment, right? And this one I will compute it again. Okay. But now let's be careful because here the bond dimension could be, we don't know what the bond dimension is going to be, right? It can grow. The bond dimension can be something that is AL minus 1, the previous bond dimension, times D. Okay? So this AL can be, can range, you can have a number of them, which is D times D. And so then as you continue to do this, the bond dimension can grow and grow. So when you do this, you look at the singular values, and you see how they decay, and then maybe you can truncate. Okay? Or maybe you can truncate even more than it was, but okay. You truncate, and then you progress. Okay? So this is quite an important thing. It allows you to increase the bond dimension, and then also allows you to figure out what the bond dimension should be like. If we were only doing single site, okay, if we're only doing single site, the bond dimension is fixed. You have small d here, big D here, big D here, and then you end up with an MPS with this bond dimension, D, 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 okay? By having two sides allows you to, expand and then try to figure out which are the ones that you should keep. Ken? Yes?
What is the second diagram actually shows?
Sorry, louder.
What does the second diagram actually mean?
Is when I first, this one?
No,
This one? Okay. So remember yesterday when I was doing the ground state search, what we want to do is you compute 2 MPS and then you can do the next and the next and the next. But when I compute these 2 MPS, the one that I'm actually going to keep is, if I'm sweeping to the right, I will keep the one on the left, okay, to update my environment. And then I will continue and I compute here are sites 2 and 3, then I compute sites 3 and 4. Okay? Makes sense? It's the next step of the iteration and the algorithm. Okay, good. Okay, so this is what the question. There was another question about what optimization method you use, okay, to compute the MPS. And I said, okay, we can use Lanchos. And there was a question, how do I, can you show us about Lanchos? And I can do that, but a bit running out of time. So I wanted to move some to the time evolution. And then if there is some time, I will describe Lanchos, maybe today or tomorrow. Is it okay? Okay, so time evolution. Yes?
In the last thing that when you have single opportunity,
Yeah.
with one physical index which is D,
Yes.
then the bond dimension, you are allowed to increase the bond dimension here.
No, how do you increase? No. Because you solve this, remember? It looks, this is equal to some E, and then your state like this, right? So once you solve this equation, you're just going to find an element, a matrix for states, which has these dimensions. The dimension was D and D, you're still left with D and D. It's not bigger. But while here, since we group these two together, okay, we build something that has AL minus 1 sigma L on the left. So the size of this matrix now is D times D here, and then something that can be up to D times D on this side here for the U matrix. Okay? So when you take the single values, it's from a range that can be at most D, small d times big D. Okay, cool. Okay, time evolution. So we have an MPS. And now we want to, let's say, psi. And we want to find out what would be psi at a later time. And to do this, we, in principle, okay, if you know what is the MPO of the evolution operator, you could apply this evolution operator. It's a U, okay? And then figure out what is the new psi, let's say psi prime, that best approximate the product between these two things. Okay. So the first thing that I would like to mention to you is why, to show you how this can become always quickly quite complicated. Okay. So suppose I have this MPO here with some some bond dimension, let's call it dw, okay? Sorry, capital DW, bond dimension, okay? So on this side here, I have dw, and here I have d, here I have d, here I have dw, okay, on this bond here, okay? Now, look at what happens when you have this MPO that multiplies your MPS. Here a bond dimension d, here you have dw, d, and then you have this one that contracted. Once you contract over this index here, okay, you can write it as this object here, fair enough. And what you can do, you can merge these two indices and write it as, let's say, I draw it 2 lines just to show you that it's a bit factor, okay? You have something like this, okay? And here the indices would be something like a combination of AL and BL. And here you have sigma, okay? Now you can see straight away that the bond dimension, if you just trivially multiply, okay, grows as the product of the 2 bond dimensions. This bond dimension here is d times dw, okay? And now imagine you apply this operator again, and again, and again. This grows exponentially, okay? So time evolution is in general very hard, okay? Of course, so what do? We apply this, and then we compress, but eventually there will be a point where the singular values don't decay well enough, and you cannot compress. And that's the problem that you encounter when you do time evolution with lattice polar states. Make sense? Okay. So this is where the difficulty is going to come from. But of course, we can try to push it as much as we can and try to describe the system as well as we can. Because we use a big D for the MPSs, and dw is for the MPO. In general, they're very different, right? Remember, for example, when we did that, okay, the operator up there, the bond dimension is 5, okay? But for your MPS, it could be whatever it is, right? Maybe 100, maybe 1, okay? Depending on the state that you have. Okay, so so this is the first thing that it's important to mention. When you multiply operators times MPS, the bond dimensions increases as the product, okay, and it keeps going. Okay, good. Now the other thing that is good to mention is, okay, how do I build up this unitary operator, for example? And I think Giacomo already mentioned this in his first tutorial. And it's related to the fact that the Hamiltonian is composed of parts that don't commute with each other. Okay, especially if I write H as sum of HLs, where HL is the bond Hamiltonian. So maybe, for example, HL could be something like sigma ZL, sigma ZL plus 1, plus sigma X L, sigma XL plus 1, plus sigma Y L, sigma Y L plus 1. Okay, some bond Hamiltonian. Maybe I can put a prefactor here, delta, to have a generic XXZ model. Now you can see that HL and HL plus 1 do not commute. Okay, and since they do not commute, then you need to do some approximations. When you yes.
So in the final diagram, there should be another leg for MPS, so where it's
This one? No, there is no leg here. Okay, let me. This one, right? No, there is no other legs. Let me go through the legs here and do the multiplication more easily. Okay, more explicitly. Okay, I have MPS sigma L, let's say prime, AL minus 1, AL, and then I multiply by W sigma L prime, BL minus 1, BL. Okay, and the solution of this, okay, you add up some over these indices, and you're left with some, let's say, m tilde, sigma L, and then you have BL minus 1, AL minus 1, which I group, okay, and then AL, BL, which I group, which is what I've written here. Is it clear enough, right? Yeah, sometimes it's useful to then write it down explicitly, and it should come out quite straightforward. Okay, so I have these things that do not commute. So now let's write graphically this bond operator Hamiltonians. And I can say something like this, right? I can write it like this with a sigma L plus 1, sigma L prime, sigma L plus 1 prime. Okay, so this is my local HL. Fine? And each local Hamiltonian, I know how to exponentiate it. It's quite straightforward. And so I can approximate U, which is equal to exponential minus high h delta t, let's say, U dt. I can approximate it as some Trotter decomposition. And here, I think it's easier. Okay, so exponential. Okay, it's easier to do. Okay, let's do it this way. Exponential minus high h1 dt over 2. So this I'm doing a second order approximation. Exponential minus high h2 dt over 2 all the way to minus high h L minus 1 dt over 2. And then I continue with exponential minus high h L minus 1 dt over 2, exponential minus high h L minus 2 dt over 2, all the way to minus h1 dt over 2. Okay. And graphically, what I'm trying to do is this. I start from my HL, and I build this operator U, let's call it UL, okay, which is also something of this form, okay. And the way I'm approximated U is graphically, it looks like this. Okay, so this is U1, U2, U3, U4, then I repeat U4, U3, U2, U1 for a 5-size system. Okay, and imagine you'll apply this on your MPS. Okay. Yes. So you apply this one, then this one, then this one, then this one, and you come back. And this, all of this, is an approximation of your U for a certain delta t. And this is second order approach. Okay, I think. Fair enough? Okay. This is quite clear, I hope. And now the question is how you actually implement it. Okay? And then let's do a first few steps, and then you can see how.
So the last one exponential of the equation that you so that should be another exponent.
Oh yes, there is an exponent here. Yeah, thank you. Yeah, it was lost. Thanks. Okay, so let's do the first step.
So L should be the weight index. So how to choose this model?
How to choose this model? What do you mean? Which model?
I mean, this,
The H1?
you're writing UDT as an approximation.
No, yes, UDT is approximated with this product of many UDT. But these ones I can do it exactly. Right? It's just a 4x4, right? I can do an exponential for a 4x4, right?
So I will apply this use, construct this use up to the mid index. I mean, this capital H, the Hamiltonian is summation over HL.
Yeah, so since the Hamiltonian is summation of the HL, okay, I cannot just exponentiate the Hamiltonian trivially, okay, it's the sum of the, but I can approximate it up to second order in dt with this formula, okay? Now, of course, I can use other formulas that can go to higher orders, okay? But in many cases, this is good enough, okay? What is the consideration? So when we multiply terms, okay, the more terms you multiply, the more the bond dimension can grow, okay? And then you need to truncate. And when you truncate, you may do approximation. Then things start to become a bit not as precise, okay? So you want to have a way to write the exponential which is, good enough. And when you take into account that the circuit that you will use is not too deep, okay? And the bond dimension may not grow too much. There's all of these kind of compromises, okay? But eventually, the bond dimension will hit you, okay? Whatever you do.
We need to construct this. We need this second order. We could have done it in the first order, starting from H1.
I don't know how to build. I don't know how to write this. I don't know how to write the Hamiltonian, the MPO that is the exponential of the full H.
Then I'm asking, we could have done this U1, U2 up to U capital and don't come back.
But then it would be first order. And first order is much, much worse than the second order.
So how the improvement is?
Okay, so you can. Okay. You can do an expansion of this, okay, up to second order and third order and so on and so forth, and compare it to an expansion of this to second. And you find that up to second order is exact. Okay, but if you do it with the other one, you put delta t instead of delta t over 2, and you stop here. Okay, you find it already, you only go the first order. Okay. Bless you. Okay, so now let's do this multiplication here. And since I'm starting from the left, what is convenient is to have everything in right canonical form. Okay, and then I apply this operator U here, right? Good. Okay, so I apply the operator, and let's call these two B's. Okay, let's call them some phi. Okay, sigma 1, sigma 2. Okay, A, L, 2. Yes. Okay. This is the B sigma 1 and B sigma 2. And now I call phi tilde, sigma 1, sigma 2, A, L, 2, equals to the operator U, sigma 1, sigma 2, sigma 1 prime, sigma 2 prime, that acts over B. Okay, let me write it with the primes here. Sigma 1 prime, B, sigma 2 prime. Okay? So once applied, here, I get this new tensor, right? This thing here. This is phi tilde. Okay? And once I have this, what I'm going to do I'm going to do, after I've done the multiplication, I do a single value decomposition of this thing. Okay? So Okay? I do the single value decomposition. This is the U. I reshape it. I get this A matrix, right? As we've done it many times. When we're doing ground state search, at this point, we will just keep this and discard that, right? But now we cannot do that. Okay? So what we have to do is to bring this to the other side. Okay, so we have we have done this. We are rewritten it as some new two pieces tensor, okay? Two of these MPS portion tensors. And then I have rewritten this as A. And then I have something here, which is strange. And then everything else, okay? So this is after the operation of the first thing. This is an A matrix. This is some generic M matrix. And then I have all the rest is my B's. Okay? This is after the operation of the first, what did I think? After U1. Okay? So these have evolved. Okay? These I kept already in A form. And then I have everything else. But this is neither A or B. Now that I have this thing here, I'm going to apply U2. Which I apply here. Correct? Okay. So then I can write, I had a phi that looked sigma 2, sigma 3, A1, A3, okay? That looked like M, sigma 2, A1, A2, B, sigma 3, A2, A3, okay? And then apply the operator to obtain phi tilde, sigma 2, sigma 3. Maybe I put the primes here so it's easier. Really analogous to what I did before. Sigma 2, sigma 3. Okay, and then here I have the M matrix and the B matrix. Okay? So once I get this, again, same as what we did here, I've done this multiplication, I will do a singular value decomposition. I will get an A, sigma 2, A1, A2 prime, okay? And then some singular values, A2 prime, and then some B, some V dagger, okay?
That should be prime, right? Sigma 2 prime, sigma 3 prime. The above line.
I put the primes here, and then so below, here prime, yes, thank you. Okay, and again, you see that you have this portion here, and this you carry forward to the next. So now the drawing, if I use this color coding, it becomes A, okay, Then you have this M, and then you have B and B. Okay? And now you apply U3, then you apply U4, and you come back. Okay? And every time you keep it, you have A matrices on one side, and you have B matrices on the other side. This keeps the central portion as a proper density matrix of the portion of the system. You can evolve it, and things run smoothly. Okay?
So like for each U1, U2, U3, first we multiply, then we take a single value. Doesn't doing that make it very like,
Yeah.
isn't that?
So it's sequential, so it's a bit slow. You need to go through everything, right? So can we parallelize it? And the answer is yes. Okay, that was exactly the next point I want to talk about. Okay, but I hope this part is clear. Any more questions on this part? Because the next part is not. It's
So after applying U2,
yes.
you don't have the same index, right? You don't have the same index
No.
because now it's
Correct.
temperature change.
Exactly. Okay. Now, can we parallelize it? Yes. All of this is well explained, at least in the Showbox review 2011. So now the point, it's a little bit tricky, but not too crazy. We start again with OBs. Okay, and can we? What we know is that if I apply these bond operators on, let's say, the odd bonds, they commute. Correct? And or if I apply them on the even bonds, they also commute with each other. So in principle, I could be able to apply them in parallel.
For a short range Hamiltonian.
Sorry?
Not for long range Hamiltonians.
Not?
Not for long range Hamiltonians because
Yes. Yeah. Then you will use different decomposition of your different authorizations, right? And so you can think of this as you will have different layers depending on the range of the Hamiltonian. Yeah. So you could do something similar to what you did there, where you apply on the even Hamiltonian for a time, also odd Hamiltonian for a time delta t over 2, then on the even ones for a time delta t, and then on the odd ones again. Okay, time goes in this direction, right? dt over 2. Okay, so then you could do this, right? And yes, and once you do this, so the applications can be parallelized. And in principle, you could say, okay, I multiply, then I make it. After that, I have all m's. There are no left canonical, right canonical in general, and then I will do some sweeping to make them canonical and then compress. Okay, so you could do this. But yes? Sorry? This one? dt over 2. When my Hamiltonian is in two parts, let's say I have h is equal to h1 plus h2, and h1 does not commute with h2. Okay, then I can approximate exponential of h. Okay, with the exponential of h1 over 2, exponential of h2, exponential of h1 over 2. Okay, which is exactly what I did here. Okay, does this address your question? Okay, cool. Okay, so you could apply this layer. Now you have a new EMS. Then you make them, let's say, left canonical. Then you come back and you compress. You go back to B canonical and so on. But you can do even better. What we can do is that given any two B's here, and a single bond Hamiltonian, okay, I can turn this into two new B's. Okay, let's say B tilde, without having to touch all the others. Okay, I can really parallelize this step. Okay, then I can just look at 2, and I make sure that, and I keep it as right canonical. Okay, this is and so then you can really do these operations in parallel. Okay, because and then you get back some B, some right canonicals, and then you continue. So how to do this is okay. To do this, let's try to think of it this way. The local, okay, so let's call phi this product of B's. Yeah. Let's say sigma L plus 1. Okay. This is not a good representation of, it's not the physical reduced density matrix when you trace out everything else. The reduced density matrix of when you trace out everything else is, I call it psi, sigma L plus 1, which is given by the singular values before this site, and then B, sigma L plus 1. Okay. So now when you apply the new operator, okay, the U operator, and I generate my psi tilde sigma L plus 1 will be the unitary that acts on psi, okay. Okay, this is the evolution of that portion of the reduced density matrix of the system, and this is given. Once I'm here, I can do a singular value decomposition. Okay, so I can write this as some A, sigma 1, some singular values in between. Let's call them lambda L. And then B, sigma L plus 1. And I put tildes to show that these are updated. Okay? So we can easily find the new B at the site L plus 1. This one, it's easy to find. I add the singular value here. I do the evolution. Once I have this, I can do a singular value decomposition. And I get the new. In parallel, okay, at the same time, what we know is that the new sigma L plus 1 is also given by U sigma L plus 1, sigma L prime plus 1, sigma L plus 1 prime, that multiplies B sigma L plus 1 prime. Okay. Now, this object here would correspond to the new B tilde, okay, sigma L, B tilde, sigma L plus 1. So what I can do is to multiply this phi tilde times what I found from the other side, B tilde sigma L plus 1 dagger. Okay? Very important. Dagger. And what this does, kills this term here, because B dagger is identity. Let me write it down. This is identity. And so this is equal to B tilde sigma L. And so we have found a way to also compute the B tilde side sigma L. Okay? Without having to do any inversions, just multiplication. You compute you do the, but the important thing is that whenever you have a system, okay, let's say in a right canonical form, for example, is the B's times the lambdas, okay, that can be used to represent the physical reducing symmetry of the system when you trace out everything else, okay? Okay, so this can be done in parallel.
How do we get psi from phi?
You need to keep in memory the lambdas on every bond. Okay, so you always keep in mind the lambdas on every bond, and then you find and you update it every time, right? As you move around, you find a new one and you update it and you keep it. Okay, and then you build it for the next one. Okay. Cool.
You said that this from phi we do this even side operation, we go to phi tilde, and then you're telling that this B tildes can be computed just by multiplying this case.
With B dagger, because we know that it's B times B dagger is identity.
Right, but by parallel you're not telling that the even side operations can be done in parallel. It's not.
You do first with the odd side in parallel, then you do the even side in parallel, then you do the odd side in parallel. Okay, now everything in parallel, I don't know what to do. Okay. Do I know to? Yeah, maybe. Okay. Good. So this leaves me for half an hour for this class. And so I would maybe pause from tensor networks and move to neural quantum states. Is it okay? Any more questions on this? Okay, so then we will have at least about 2 hours, between half an hour today, 1.5 hours tomorrow, to talk about this newer method, okay? Okay, so neural quantum state, it's a variation of Monte Carlo approach that started with a beautiful paper that appeared on the archive in 2016 by Giuseppe Carleo and Matthias Troyer, okay, which was published in Science in 2017. And yeah, I think it kind of took at least my community by storm, and already then they showed some quite nice and promising results, and now it's almost 10 years. Wow, time flies. Now some state-of-the-art results on ground state search, for example, they are obtained with this method, okay, as beaten other methods. So it's really, really nice, and there is a lot of people working on it in different parts of the world. I'll probably not make justice to mention everybody's contribution. Today I will try to give you an idea of some ideas about how you do ground state search, or see how far I can go in half an hour. And then my objective is to get you also for neural quantum states to do some time evolution, to show to you how time evolution can be done. And there are also very nice results and new results in that direction. And very, very recent. And yeah, it's still very exciting and thriving area of research, especially with the new updates that there are in the neural networks community, in the classical neural network community. Transformers are getting more used more and more also in the condensed matter physics community now to represent many-body wave functions. And then GPUs are getting more powerful and more expensive. Yeah, but it's very exciting. You can get a GPU with 80 gigabytes of RAM and these kind of things. There's a lot of things you can do. Well, yeah, it's a lot more expensive though, but it's needed. Okay, so let me try to give you some ideas. And not just expensive. If you live in some countries, you may not even have access to certain GPUs, right? So it's a really complicated business. Okay. Okay, so the basic idea is that it's a variational approach. Okay, so similar to what we did just now, it's a variational approach. But for tensor networks, you were able to sum over all the possible sigmas. You remember? We were summing over all the sigmas because it has this beautiful, especially for matrix polar states, has this beautiful, efficient way of contracting all the tensors. Okay. Now we will not be able to sum over all the possible configurations, but what we're going to do, we are going to sample from the configurations, and you try to sample from the configurations in a way that is, follows the probability distribution of your wave function. Okay, and the more accurate we can do this, the better it is. So it's a variation of Monte Carlo approach, and you start from, since it's variational, you start from an ansatz, and the ansatz it's some function with some parameters, let's say theta. Okay, and you get in an input, which will be your sigmas. Now I think for simplifying, in this portion I will use x. Do I use x? Yeah, let's use x for the configurations. Okay, and for spin ups we will label the x to be 1, and for spin downs to be -1 in many cases. But okay, that is not super important. So you have a function that has some parameters theta, gets as input a configuration, and gives you some output, okay, which in many cases could be, for example, the logarithm of, which is proportional, okay, to the logarithm of the wave function. Okay, let's just say. Okay, something like this. Okay, but in principle, this can be just is something that belongs to complex numbers. Okay, is some complex number, and all you need really is something that spits out a complex number. Okay, and now then the question is it representative enough? Okay. And then can it be trained? Okay, can it be optimized? Can I find what are the values? So these are different questions. Right? This one is saying, is my variational ansatz expressive enough that I should be able to represent whatever wave functions I need to represent, okay? And the other one is, am I able to find the right parameters for this network, okay? And hopefully, can I do it efficiently, and can I have very little parameters and try to describe something complicated, okay? So this is the idea, and no. Okay, let me. let me write this, and then it will be clear. Okay, so let's say I want to compute an expectation value. Now assume that actually the wave functions are not normalized, and in fact the output of the neural network will be some numbers, and it will be proportional to the wave function, but it will not be in general normalized. Okay, so this, if I spell it out, is the sum of x prime of psi x, x h, x prime psi divided by sum of z, okay, psi z psi, okay? Then this, I write it as some psi theta of x conjugate. Okay? Because given a configuration, I need the complex number that comes. Okay? Then h x prime is just our Hamiltonian elements, okay, in the computational basis, and then psi theta x prime. Okay? Again, I just need a function that given x prime, it gives me that complex number. Okay? And then I divide by sum of z of modulus of psi theta z modulus square. Okay? Nothing shocking here. Now, what we're going to do, we're going to multiply and divide by psi theta x. Okay, same configuration as this one, and divide psi theta x. And you could start to be worried. Say, hey, but this psi theta x could be 0. Huh? Okay, the problem will be solved very soon. Don't worry. We don't need this theta. What do you mean? Theta is the variational parameter. So, okay, let me give you a very simple example. Okay, just for a variational ansatz. Okay, I have like similar to what Giacomo did in the tutorial. He gave you Gaussians, right? And so, given I can give you a parameter. Okay, and then you can write a non-normalized Gaussian will be something like this, minus x squared over 2 sigma squared. Okay? And then you want to minimize over sigma to find the ground state, to find the sigma that corresponds to the ground state of the harmonic oscillator, for example, right? So that's the idea. What you want to find is sigma. Okay? And this is a variational ansatz, which is not normalized. The idea is very, very, very similar to this, okay? But since we will live in a space where x can take an exponentially large number of different configurations, okay? We don't have a way to sum over or check all of them, okay? So we will sample from them, but I will get there in a moment, okay? But this is kind of the idea, very similar to some of the things that we'll see. Okay, so now that we have this thing here, I can merge some of these things, and you realize that I can rewrite this as sum over x, okay, of this is psi theta x modulo square. Then this, I bring it inside here. Okay. That multiplies sum over x prime of h x prime psi theta x prime psi theta x. Okay? I just move things around and group them. Okay. Now, what we realize is that this portion here is just a function of x because I summing up over all the x primes. And I call it, okay, it's been called E log of x. Okay? And this, if you look carefully, okay, this is the probability amplitude of one configuration divided by the sum of all the configurations of the probability of one configurations divided by the sum of all the probabilities, or the probabilities of all the configurations. So this is basically the probability of x. Okay, so this is P of x. And then you sum over x. Okay, so we can rewrite the expectation value of the quantity of energy as probability of a configuration times this quantity E log of the configuration. Good. At this point, you can what you do is to, if you can sample from this configuration, okay, this will be approximated by 1 over number of samples, sum over x of E log of x. Okay? And this is where the Monte Carlo portion comes from. So instead of summing over all the x's and looking at their probability and estimating, doing the expectation value of this, you sample from this configuration, and then you approximate the energy. Okay?
So each x prime, so looking at the configuration, so if I hit my Hamiltonian on Ax, then it can get at best L number of states if it's a local Hamiltonian. Then I have to look for those configurations and make this local.
Okay. So you have yes, very good point, and I wanted to get there. So x as how many of them there are? There is 2 to the n, right? X prime, how many do you have? 2 to the n, right, for spin-house. But how many sums do you have to do here? Not many, because this, in general, is sparse. Okay? So then that's why it's possible to do it, because H is sparse. We will see tomorrow, hopefully, when we do the time evolution. Okay, let's say you can do u of this. Okay, then it will not be sparse. There will be, but we'll get to that tomorrow. Okay, so far so good.
One small doubt. In the beginning, we said f theta was this log of this thing. Why should it be log of something and not?
I will get there later when we optimize. So there are various reasons, but when you do the optimization, you will see that the derivative of the log is actually very useful. Okay, and the other thing is that if you can accurately predict the log of psi, then you can have very good values also for when psi is very small. Okay. Okay. So this is the first thing. Yes.
Given a psi,
Given a psi, yes.
how to choose or how to think about that? What is the reasonable candidates for the sample space? We cannot sample all over the configurations.
Yes. So given a psi, you may start from a wrong psi. Okay, you just, maybe you, whatever, you put some random parameters in your network. Okay, then you definitely don't have the ground state in general. Okay, so what you do, you still compute p of all of you still sample from this wrong configuration. Okay, and then you try to see how do I change my parameters theta such that I can decrease the energy. Okay, and by doing that, you have a mechanism to update your thetas and get a better psi. And then you continue until you reach close to your ground state. Okay? So this expectation value here, okay, is going to be what call it like some loss function C. And then you minimize. Okay. Now this is unsupervised machine learning, right? Because you're not putting in data and you say, okay, I know that psi is this value here, psi for this configuration is this value, psi for this configuration is this value. It's just an optimization, update, okay, of the parameters. Okay. So at this point, there are a few things to say, and then maybe I only have 9 minutes. Let me just say a few things. Every time you do this, you get the energy or whatever observable. Since you're doing Monte Carlo, you don't get it exactly. Okay, you will have some noise. Okay, and now you will get noise also for the gradients that bring you down to the ground state. And if this noise doesn't decrease, then you will not be able to reach the ground state. What we notice is what is useful is that the closer you get to the ground state, usually the noise tends to decrease. And one way to see this, although it's not the best, we can do better. I'll just show you something very simple. Is that, let's say psi is really the n-eigenstate of the Hamiltonian. Okay, I managed to find the thetas such that psi is one eigenstate of the Hamiltonian. It doesn't even need to be the ground state. What does it mean is that if I multiply, so this is eigenstate. Okay, then as you look at E-log, which is sum over x prime of h x prime psi theta x prime psi theta x. Okay, as doing like backward what we did before, you can see that this is equal to sum of x prime of x h x prime psi x psi. And since you're summing over x prime, this is identity. Then you get psi h x h psi over x psi. Okay, and this is exactly the an eigenstate of the Hamiltonian. This will be E. Okay, let's say En x psi divided by x psi. These two cancel, and this is going to be equal to En. The main point here being that whichever x you choose, okay, to compute E-log, whichever x you choose to compute E-log, you get the same value. So the mean is very well determined, okay, and the variance is 0. Okay, so as you the eigenstate, each eigenstate has 0 variance. Okay, and so actually looking at the variance of E-log as a function of the different x's that you can sample, you're sampling from, it's a very good idea. It gives you a very good idea how far you are from the ground state. Okay, and there was a nice work, 2024, I think, or maybe 2025 has been published, but I think it came out in 2024 by many people. The first author was Tian Wu. Last author, I think Giuseppe Carleo, on Science about var bench, where they use this also to estimate how accurate, how difficult the problems are and how close you are from the solutions. Okay, so this is a very, very important point. Yes?
Does it only goes to the ground state or can also be stuck into other eigenstates also?
Okay. Well, in general, if you minimize, unless you are orthogonal to the ground state, you will get there. But of course, you can get stuck. Okay, and every nonlinear, this size are nonlinear. These optimizations, you can have many problems. Okay, but. And one way to solve this problem is to have really good optimization approaches. And this actually, so I wanted to show you the gradient in general, and then a very good way to find the ground state is called stochastic reconfiguration, which was built by Sandro Sorella, and that is also very, very useful for this. So let's try to get the gradient. Maybe I bring this down. So you have this expression here. I just need that. And then I try to solve it here in 3 minutes. Wow. Yes, we can do it. Okay. Let's go. I will give you the gist how it works, and then since some of you probably will be confused, I will start from it tomorrow, and then and tomorrow I will finish you off. Okay. Okay. So yes, sum of x prime of psi x theta star h x prime psi theta x divided by sum of z psi theta z modulo square. And I want to minimize this thing, so I will take the derivative of d theta of this thing. Okay, now I'm assuming thetas are real. Okay, it's actually kind of fine for many problems. You can extend it to complex quite easily. Well, not super easily, but quite easily. Okay, so now you have theta appears here. So you have to do derivative of different places. And now the trick and why the logarithm is useful also is when we take the derivative of d theta, let's say of psi. Okay, what we're going to do, we're going to write it as psi theta derivative of a theta of ln of psi. Is actually the same, right? Because when you take the derivative, you get the psi derivative of psi over psi, and it cancels. But this will be useful because then I can still keep the psi that we will need to build the probability to do all the things. So once you do this, okay, I'll just give you the final answer, and tomorrow maybe I'll do the derivation. So from here you will get. Okay, I do not know how to give final answers. D theta star, okay, h x prime psi theta x divided by whatever is here plus sum of x prime psi theta x h x prime d theta x psi theta x divided by the denominator. Okay, so you have these things appearing, and then when you have the derivative of the denominator, get 1 over minus. Okay, 1 over this square. I will keep 1 here, and then they are both. So you have some x prime of psi h psi. And then the derivative of this is sum of a z of this thing, and then you have sum of, let's say, y of modulus of psi y square d star plus d. Okay, so you have these appearing. This comes from taking the derivative of the denominator, you get 1 minus this square. I put 1 here, I put 1 here. Okay? This is just carrying it to this side, and then I take the derivatives. Okay? It's a bit fast, but you're good. And this doesn't move. And so, once you group everything, you find that this gradient is equal to E log x d star x, this expectation value, minus E log d star x. Okay, and you have C1 and the complex conjugate added up, so you can do the real part of this. Okay, so you have an expression for the gradient. And the way you can update your theta, okay, so you have your theta tilde, okay, will be equal to your initial theta minus, okay, some learning rate, okay, and then this, let's call it F. Okay, this thing, let's call it F. Okay? And this is how you update your, okay. And as I'll show you tomorrow, this doesn't work very well. Sorry?
X and X primes are not X primes.
There is all, it's all taken inside, right? I'm summing over the X, and then I will take the expectation values. Once you have this, I can still do multiply and divide. Okay, maybe I should do this tomorrow, but you multiply by t theta x, divide by psi theta x. And then here you have your probability, and here you have something slightly different from E log, right? So it's E log times this thing. Okay, you see it? So you get this expression. And then, pum, pum, pum. So you have a way to optimize it. Tomorrow I will show you stochastic reconfiguration and then time evolution. Sorry, I took 2 more minutes.
So is there any questions?
This d theta is what the derivative?
Huh? This F is the gradient of the energy. Okay? So I will update the theta so as to reduce the gradient of the energy with a certain learning rate. This thing is the learning rate. And this thing will not be, depending on how many samples you take, this will be more or less accurate, okay?
So d theta means the derivative of log of psi theta.
This d theta. Yeah, it's defined here, right? Where I defined it? I thought I defined it somewhere. Did I erase it? Ah, yes. Okay, sorry. It's this thing here. I wrote it, but I didn't. Okay, so this thing here. Okay? Yeah, sorry, I didn't. I assumed I derived.
If you have this theta vector as a multi-component object,
Yeah.
rather than a single variable, then what do you look at? I mean, you could have minimized this to theta 1, theta 2, theta 3, and so on.
Yeah, so you have a large number of thetas, and then this theta is for many thetas and for many x's. Okay? So for all the x's you sample, you have a different d theta. Okay? It's a function of x. And tomorrow when we look at the stochastic configuration, maybe some other tricks like min SR, maybe I'll show you how to do these things efficiently. Okay. We'll have a full menu for tomorrow as well. Cool?
So if no question, let's thank the speaker.